All right, so back in the world of CFA. Let's start with opening for questions, because I had one question I want to answer that came in over email, but anyone else want to talk about anything in particular? Things you've been chewing on that don't make sense yet? No? Well, I will let that percolate then, and we'll go to the question that I got. I'm going to say it correctly. Amalari? No. Amir Ali. Okay, I'm getting closer. I guess got to keep working on it. So he sent me some questions over email that I thought would actually be useful to discuss as a group. So I'm going to pull these up here. So number one here. Because items in CFA have to be continuous, does that mean the scale of the factor will also be continuous? The scale of the factor will always be continuous, irrespective of the kind of items that you have. So the latent trait in question is continuous and normal, no matter what. It's the item responses that can vary in kind. But then, follow up to that, I know we set the scale of the factor to have a mean of 0 and a variance of 1, yes, but what is the actual scale? That's it. It has no actual scale. It's whatever you set it to. So you can set it to borrow the scale of an item by fixing a factor loading for that item to 1, and then it borrows its variance as the part of the item that has the part of the item's variance that's due to the factor. You can do the same thing on the mean side, where you borrow the item's intercept to become the factor mean. But honestly, it's latent. It's never going to have its own scale. So you can set it to be whatever convenient metric you feel like having. There is no inherent scale to it. It does, in theory, go from negative to positive infinity. In practice, though, it's constrained by the number of possible response patterns. So what you'll often see at the end of, let me pull up a picture here. In example 4, we will see this here, hopefully get to that point today, but towards the end here, yeah. I outputted predicted factor scores for the two factors that we're going to end up with. And just as an example, you can see how the left side of the positive distribution here sort of trails off, but the right side doesn't. It stops abruptly, because those are people who answered 7 to all 3 questions. And the right side cannot spread itself out if there isn't variability with which to differentiate people. So in practice, you end up with these truncated distributions because of lack of reliability, essentially. But in theory, it should be able to go the whole spectrum. Okay, helping so far? Okay, good. There has to be a cutoff at both ends somewhere. Yes. We don't determine that, the items do. So in this type of situation, if you're looking to be able to spread out the people at the ceiling, you need to add either more items or more response options with which to spread them out. So I think the top end of this is like almost always or something. You'd have to add an absolutely all the time option, an 8, so that people could pick it or not to spread themselves out, or add more items with which they might pick something lower than 7 to differentiate themselves as well. I won't say, yeah, I can't say cutoff point, because it depends on what people say to the items. So I will show you factor score distributions that are completely not normal, because that's the way the people stack themselves up, even though the model is assuming that it's normal. So if you have a ton of people, for instance, who answer the lowest option, you are going to have a giant pile in your factor score distribution that corresponds to those people who all answered the same lowest item for every item. There's nothing with which they can spread themselves out. The only reason that we actually have a factor score estimate for people who have all the lowest or all the highest is this assumption of normality. It's essentially a prior distribution. See, Tyler? Bayes. It's a prior distribution by which, if we assume that the distribution for these factor scores is normal, you can come up with an estimate, even though in theory, like it would be, you wouldn't know how high someone is if they pick the highest number for every single answer. So it's not 3 standard deviations per se, but there will be an upper bound based on the data that you have, and a lower bound as well. Next question. Can you give me an example of a latent trait that has a continuous scale? So do you mean a response type? Yes. I've only seen Likert scales in surveys. Yes. That is most common. However, performance-based items like response time, if you're measuring something like processing speed, a lot of the time what you do is ask someone to do something as fast as they can. Response time to the item would be used to indicate a trait. There's also, I'm familiar with the Tower of London task, a measure of lots of different things according to who you ask, but latency with which to make your first move is the outcome for that task a lot of the time. It's one of those, like, you have like stacks of blocks and you have to get the blocks across the different towers in so many moves kinds of things. So you're supposed to think about it and then decide what to do as opposed to being impulsive. So how long it takes you to make your first move would be another one. So examples with time would be something that would be continuous. However, in those cases, you're likely to have a skewed distribution, and people would probably do a natural log transform to sort of reel in the tail on the response time to make it something where your model can still be linear, but you would be predicting an exponential curve when you back translate it out into original response time. The cancer predictors? Yeah, so like percentage white blood cell counts or something. Yeah, I mean, there's any kind of data can be an item per se. If it's not self-report, if it's performance, you have more options for something that would look more continuous, I think. Also, Mayumi's not here. I was going to use her slider bar. She's coming. Okay, well, when she gets here, she's going to give her slider bar example to help answer this question. So, sorry. Oh, just threw up in my mouth a little with that question. No, because parceling is cheating. And that means 3 people didn't know the difference. That's what peer review means. No, so parceling is the process by which you add some items up and then you call it a new item. And that item will be more normally distributed than the original item. However, what did we learn about alpha, for instance? When you do alpha reliability, what are you assuming? There's one, unit dimensionality. All the items are equal, right, and they're uncorrelated. So you are assuming one more thing, which is parallel items, I think, which is equal error variances when you add stuff up. And it's not tested, right, because the sum doesn't know how it was created. So if you wanted to test a parcel, the last 2 slides in Lecture 4 describe how you would actually test those assumptions of equal loadings and equal error variances that you are assuming without testing when you parcel. So, yeah, no parceling is cheating. And there are a number of papers that I can show you that have indicated that the way you decide to combine items can give you completely different answers. And so there's an arbitrariness to it also that is a little bit disconcerting. The data that I have is a Likert scale. Does that mean I cannot use CFA? Great question. Depends on who you talk to. So there's a whole lot of literature looking at how many item responses is enough to pretend it's normal and continuous. It has to do with not only the distribution, but also the shape of the distribution. So you can have a 9 response option item, but if people don't make distinctions reliably between those 9 choices, 9 is not any better than 7 or 5. Also, if you have an item where the distribution looks like this, here's everybody who picked the lowest one, and then some sort of distribution after that, what we would call zero inflated if this were a count. Having 9 is not going to make this normal, right? You have to deal with this pile. And the problem that non-normality creates in CFA is twofold. One is just the model, the height, the thing that's trying to be maximized is based on the formula for a multivariate normal distribution. So to the extent that the data don't fit that distribution, that formula for height is not as valid as it could be. So we might be coming to a different conclusion than we should. And that affects like the standard errors of things. It affects your measures of fit, your chi-squares for the differences between models and that kind of stuff. But a bigger problem is that when you have data like this, a model is still going to try to fit a linear slope. So I'm drawing here the factor on the bottom, y on the y-axis, and to the extent that most of your data is down here, it's going to tilt it so that it's going to want to go out of bounds. And so the linear assumption of how the factor predicts the item is really the reason why CFA is not as useful when you have data that look like this. That being said, that is the way easier in most cases in terms of estimation using full information maximum likelihood to fit a CFA model than the alternatives. And that's why people really want to keep it. Plus, when you take structural equation modeling, almost always the classes start with path models, then they go to CFA, and then they use SEMs, where you're building on the CFA framework. And you're not told what to do if you don't have normal and continuous data, because that's a whole separate class called item response theory. So that's why I teach the way that I do, is because I want you to be able to pick whatever kind of measurement model fits the items you have, and then you can put your structural equation model on top of it. Doesn't have to be a CFA. No one would call it that, but essentially you can do SEM with any kind of measurement model. Okay. How'd I do? Good? Okay. All right. Who else wants to ask questions? Follow-ups on any of this. Thank you for letting me go over that. It would have taken me at least 15 minutes to type that email anyway, so I figure this is a better use of time. But no? Okay. Well then let's do a little review, dive back in. So I looked at your quizzes. For the most part, things went well. Just making a few distinctions. Let me find this picture I want here. It's this picture. Slide 10. We'll review this one more time. So two types of things being estimated, parameters being estimated, measurement and structure. Measurement is item things, loadings, intercepts, error variances. Structural model then is factor variances, covariances, and means. So when I say structural equation modeling, what we're talking about is this part, the structural model. It's the idea that these latent factors that you're carefully building are going to predict each other or correlate with each other or otherwise be associated in a way that would allow you to examine that relationship more powerfully because you have ostensibly removed all of the measurement error from the items in doing so. So you're looking at just the pure relations of the constructs at that point. So what this model is doing, even though we think of it as a regression type model where the item response for each item for each subject is a function of an item intercept, an item loading, the subject's factor score, and a residual that is the unique combination of item and subject, even though we think of this as a regression model, what this model is actually trying to do is predict the item variances, covariances, and means. That's what it's really doing behind the scenes, and that's the point. How it predicts the covariances is indicated by the path diagram here. So the relationship between two items on the same factor is whatever this unstandardized loading is for the first item times the variance of the factor times the unstandardized loading for the second item. To get from one item on one factor to one item on another factor, all the cats in the world are going crazy now among my legions of fans. To get from 1 to 6, for instance, it's the loading of the first factor, the covariance between the two, and the loading of the sixth to get over here. So this model is saying that the only reason that items from the same factor were related is because of the factor. So once you control for F1, Y1, Y2, and Y3 are independent. That's a testable assumption. Likewise, The only reason for why 4, 5, and 6 to have been related is because of whatever F2 is. And after you control for that, their residuals are unrelated as well. And then one more, the only reason that items from different factors would be related is because their factors are related. And so all of these cross residuals are unrelated as well. Testable assumption. So when you put it all together, you end up with this bad boy right here, the variance-covariance matrix across your items, where the diagonal is given by the factor loadings and the error variance. Summing loadings are multiplied by the factor variance, then the error variance comes in to fill in the gap. You get your original variance back. The covariances are predicted as such. When it comes to room for misfit, it's all about the covariances. So long as each item gets its own intercept, the item means are fine. Don't worry about them. So long as each item gets its own residual error variance, the item total variances are fine. To the extent that you estimate fewer factor loadings than you have covariances, that's where you have the potential for misfit. And I think everybody got this right, the idea of estimable and testable. Estimable means you have 0 or more degrees of freedom, meaning you are estimating as many or fewer parameters than you have pieces of data. So 0 degrees of freedom would be 3 covariances and 3 loadings. That would be if you had 3 items measuring 1 factor. Estimable and testable means degrees of freedom are positive. You haven't estimated as many things as you could have. So if I have 4 items, that's 6 covariances, 4 loadings, I've got 2 left over. So what that means then, let's say that there's a debate in my field about whether I have 1 factor or 2 characterizing my 4 items. I can add a second factor and compare the fit to the original 1 factor model. That takes up 1 more degree of freedom. To the extent that 2 factors fits better than 1, that supports the argument that these are actually measuring 2 things. So there's room to be wrong. There's room to add stuff to your model to try and make it better and see if you're right. Okay. Questions on that? Okay. Sure.
So let's say you have 6, no, let's say more than that. Let's say you have 10 items.
Okay.
But you think that, or you want to test the possibility that 9 of them measure one thing and 1 of them measures another thing. You can't really do that, can you?
You could test whether the 10th item's loading is 0. Basically, that's how I would make that argument, is if that loading is much smaller than the others or non-significant. So you could set up a contrast for whether it's different than some other number or 0. Something like that would work. So model fit then. Here's my crappy paint drawing. I saved it. Just like all of the artwork I have from my son where he scribbled all over everything. I feel compelled to save it all. It's currently sitting in a big grocery sack because I don't know what to do with it now. But these are heights, right? The idea is that the object of the game is to make your data as tall as possible. So there's 2 things to think about here. One is in getting your model parameters, it tries out as many different versions as it needs to try and figure out what combination makes your total sample as tall as possible. That's how it determines the maximum likelihood estimates. Then, given that you've come up with the best version of your model, how does your best version of your model compare to the absolute best model, saturated, H1, everything gets to be what it wants, all variances and covariances estimated directly, separately, perfect. How does your HO model compare to that perfect model? Can HO ever fit better than H1? No, it's the best. But what are we hoping for in comparing them then? Non-significant difference. Phrase it using the words better or worse. Not worse, yes. We're asking whether H1 is better than HO or whether our HO is not worse than H1. H1 is it. It's the best. So all of our measures of fit are going to be relative to either this best possible model. That includes the chi-square that you get on your output, which is the rescaled difference in height between these two. And the chi-square is distributed as a function of how many degrees of freedom you have left. And the other fit measures are relative to this short little model over here, which is the worst possible model you would entertain for these data. Each item still gets its own intercept and variance, but all the covariances are forced to 0. It's saying there are no relationships here. That's called the null model. And the alternative measures of fit, such as confirmatory fit index, CFI, TLI, also known as NNFI, anything that has FI in them, fit index, is relative to that null worst ever model. Any index that has the word error or residual in it that you want to be small, those are all going to be relative to the best model. So you want the smallest difference relative to the best model, and the biggest difference relative to the worst model. So I think we started looking at fit towards the end of class in our example. So just to give you a review here, we are estimating right now, testing the hypothesis that 6 items are measures of one trait. Let me review the code here. For convenience, I have identified my factor to have a mean of 0 and a variance of 1, and estimated all the loadings, intercepts, and residual variances. Question in the back. Justin. Mm-hmm. HO. Mm-hmm. I think I know where you're going. Are you asking, like, if I say something fits, do I have to reference it relative to both endpoints? No. They're different things, and your fit indices may not agree because they're different things. So it's not that HO is, how do I put this? I try to stay away from the word explain because that's not what we're trying to do. We're trying to match. So I don't know why it is that people have different factor scores. What I'm trying to see is whether or not the covariance pattern in my items is consistent with the factor model that I put on it. But it's not explain in the sense that I know why someone has a higher factor score or another. I just know that there is a factor. So what we're trying to do is match the pattern. So H1 has the pattern in the data. How well does our predicted pattern match the real pattern? Does that help? That's really what the question is. The other comparison is it's important to know it because that way you know why some of the fit indices you want them to be big instead of little because it's a different comparison. But really this is a straw man. Like you would never think that there are no covariances in your data. And if you're right, then you have no point in doing any of this because the whole point of the factor model is to match whatever covariances there are in your data. If there aren't any, game over. Okay, so 1 second. Does that help?
Yeah, I mean, I guess just thinking back to it, but
the OLS, I do say explain, right? When you put an X in the model, you're saying, why do some people have higher Ys than others? Because of X. We're not doing that. I'm just saying, what is y? What does it look like? Okay, your question. So I have an analogy maybe.
Just sort of related. So then the idea is that you can be significantly better than worse and significantly less good than best, right? Like you can be
yes.
better than
Yes.
worst and not as good as best.
Yes.
Yeah.
Yeah. Yes, that's it. So, did any of you watch the show Susie Orman on CNBC? No, do you know who Susie Orman is? Yeah. Yeah, no, she was like a money guru that went on Oprah once and became super famous for being a money guru, and she has her own show on CNBC. And that used to be one of my go-tos when I was feeling bad about myself, because I was doing so much better than the people on that show. They would call in with money problems, and it's like, well, I have $75,000 in credit card debt, and I just lost my job, but I really feel like buying a boat. Do you think I can afford it? And I'm doing better than that guy. But she would counsel people sort of like who were so deep in debt, they hadn't been opening their bills for months, and it's like, where do I even start, right? And so step one was not to start paying off your debt. Step one was to open all the envelopes and figure out exactly what you have in front of you. That process of figuring out how much you owe each bill collector is a logical prerequisite to then coming up with a payment plan, where you then actually, in theory, write checks to these people and see your balances decrease. What we are doing here is the first step. We are trying to get organized and figure out exactly what kind of pattern we have in our data or our bills, and the structural model, the job of that is then to pay it down. So we're just trying to figure out which items go with which factors, and then we would see how one factor predicts another in the sense of, why do some people have a higher F2 than other people? Well, it's because of F1. But we can't say those sorts of statements without knowing whether or not F1 and F2 are measured by these items in the first place. So it's really just about the pattern. We're trying to match what the pattern is so that we can then explain it later on and have it make sense. I miss Susie Orman. That was one of my go-tos, as I said. But so I don't know if that helps, but it's a different kind of thinking than you're used to in stat models. The goal of this is not to explain. This part is just to figure out what you have so that you can say then later on how your factors relate to each other in the same way that you would talk about observed variables in any kind of regression or linear model. Yeah, it's different. Yeah, it's a different ball game. It's what? Stuck in a loop. Yeah, it's okay. You can get out of the loop. So yeah, we don't know why some people are higher in forgiveness. We just want to know whether we're talking about one kind of forgiveness or two kinds or three kinds, or whether our items have anything to do with each other at all. Like, we're just trying to figure that part out now. So we fit a one-factor model. Just to review the syntax, you name your factor. By is how you tell it which items are to load on it. Stars indicate free parameters. Putting your variable inside brackets is referring to its intercept or mean. Listing your variable all by itself is referring to its variance or error variance. Listing your factor all by itself is referring to its variance or error variance. In this case, this @1 means I'm saying make my factor variance 1. I'm setting the scale, I'm identifying my factor, and likewise, putting the factor variable name inside brackets is referring to its intercept or mean, and I'm saying make it 0. So my factor is distributed like a z-score. So then we looked at the solutions. We've done that a few times, focusing on whether or not we have fit then. So this is page 5, 6, top of 6. Number of free parameters, that's number of estimated parameters, meaning free to not be 0. It's 18 because we have 6 items, and each item has 3 parameters: intercept, loading, residual. Here's my HO height. It's in logs, which is why it's negative. Do I want HO to be bigger or smaller? likelihood. Do I want it big or little? I wish I were a little bit taller, bigger, yes. So that means less negative, heading up the number line. Here's H1. H1 is, in fact, less negative than HO. Our scaling correction factor, that's MLR, robust maximum likelihood. That is roughly an index of how far off from multivariate normality our items are. It's actually queuing in on more kurtosis than skewness. And it is used to correct our chi-square test as well as the standard errors of parameters for that deviation from normality. AIC and BIC are information criteria used to compare non-nested models, and smaller is better in these, just for fun. So this 307, this chi-square tested model fit, that is the difference between HO and H1. So whether or not our chosen one-factor model is not worse than the perfect model. That's what this is testing. So the null hypothesis here is that it is not worse. They're the same. And the fact that our p-value is significant to 4 decimal places means what? Worse. Yeah, our model is not as good as perfect. Sure. So this 307, that is a chi-square. It is the difference in height between the HO and H1 models. It's how much shorter our HO model is than the perfect H1 model. Significantly shorter, significantly worse. So here's where the math for where that 307 came from. It's also in your spreadsheet. I showed you then how to fit the H1 model, just in case you ever wanted to know that. Then we get to the rest of the one-factor fit statistics. So our MSEA is relative to the best model also. You want this to be small, less than 0.05 would be nice. It's 0.17, so that's no good. CFI, TLI, those are relative to the worst model, the null model. I'll put that back up here. Relative to this short one here. So you want them to be big, and you want them to be above 0.95 or so, and they are not. Root mean square residual, that is relative to a saturated model as well, so you want that small. You want it less than 0.08-ish, I think, 0.05, somewhere in there. And this last one you can pretty much ignore. The last one is the difference between null and saturated. So there are very few situations in which that would be of interest. So this tells us that our model is not very good. It's like, well, now what? How do we fix it? We got to figure out what to do. So some of you have kids, right? Raise your hand if you're a parent. 1, Tyler, and your kids aren't even in school yet, so this analogy isn't going to work. Okay, so pretend that you have kids. They're latent. They are unobserved. Here's report card 1, and here's report card 2. So what if you came home, your kid came home, brought their report cards home, and they had a 3.0 GPA. That's not bad, right? That's, you know, I might want to help them. And so the question is, well, what kind of help do you need, bud? I would have a very different strategy if the report card was like this, AAAF, then straight Bs. They're both 3.0s. So now what? I'd be like, what is this F? Is this art or is this something that matters, right? Is this like, did you flunk recess? Sorry, I'm a pragmatist. Pragmatist, yes. It's like, what is the F, right? Because that is clearly pointing to some sort of hole where they would need very specific instruction versus sort of general misfit. So this process of trying to figure out why your model is broken is what's known as local fit. And that's what you would do next. So even if your model is in pretty good shape, you'd still want to check local fit just to make sure you haven't overlooked anything that could be meaningful. So that's where we'll pick up then today. We get to, so 4 steps in model fit. We've done the first one, global. That's what we're talking about now. Does my predicted covariance matrix match the one in the data? That's global fit, absolute fit. Next up is local. So when we start on, so this is a summary from assessing global fit. It's all about the covariance and whether or not the loadings match those covariances. If model fit is not good, here's what we do next. So your author, your textbook author, this is slide 52, we're getting there, calls this localized model strain. So a local misfit, that's what we're looking for here. So we're trying to figure out where we're off. So I have a pattern of covariance that's predicted by my model, and I've got the real one. I can literally take the difference and see where I'm off. So if I did that, I did do that, in fact, for sake of demonstration. So I'm in the spreadsheet that goes with this example, and in the single factor model spreadsheet. So here is the original observed covariance matrix for my 6 items. That's H1. That's my data. Here's what my model says it should be using the loadings. So for instance, this covariance is predicted from the loading of item 2 times the loading of item 1, and also it would be times the factor variance, but that's 1 in this case, so I didn't put it in there. And each other one, you can see that that's predicted from their combination of loadings. The diagonal are the variances, and that's predicted from the loading for that item squared times the factor variance, which is 1 in this case, plus the item's residual variance. So here, up here, data, H1, best possible. Here's my version from the 1-factor model, and here are the differences. So note the diagonal is perfect, no difference. Factor variance and error variance together will perfectly reproduce the item variance, but where we're off is in the covariances. Now it's kind of hard to tell what these numbers mean because they depend on the scale of the original item. So you get different numbers if you have a scale from 1 to 5 than from 1 to 7, for instance. So rather than looking at these in a scale of covariance, it can be easier to look at them in a scale of correlation. So I did the exact same thing in parallel here. Here's the original item correlation. That's what H1 gives me. Here's my version of the pattern of correlation. That's what my standardized loadings give me. So same idea. The standardized loadings multiplied together give you the expected correlation from your 1-factor HO model for any pair of items. And then here's how far off we are. So if I go to my favorite trick here, conditional formatting, that makes it a little easier. This is how far off. So in this case, yellow is good. Green and red are both bad, but they're bad in different directions. So if I look at the first green one here, items 2 and 4. Item 2 and 4 are correlated in the data 0.57. My model said they were only supposed to be correlated 0.285, and the difference between that is 285. So these items are more related in reality than what my model says. They want to be more together. The residual correlation, and by residual I mean leftover, the discrepancy the discrepancy between H1 perfect and HO mine, the discrepancy is positive. That means the items were more related in the data than what your model said. And you'll note the pattern. The same thing happened between 2 and 6 and 4 and 6. Do you remember what those even-numbered items have in common? They were the original. They were positively worded. Likewise, here's a red one. 1 and 3, 1 and 5, and 3 and 5. Those aren't very far off. Those were the reverse-coded ones. So the model did a better job of accounting for the covariance between the reverse-coded ones because those items had stronger loadings. So if I go to the standardized solution right here, item 1, item 3, and item 5 had the 3 highest loadings. So their covariance is already being pretty well predicted by the factor model. They are driving the factor model. So even though I'm thinking of this as forgiveness, what this factor really is, if you look at the pattern of the loadings and which ones are relatively more important, what this factor really is not unforgiveness. That's what those items mean when they're reversed. So where the factor whiffed, another technical term, is in the positive ones. They are more related than the model says they should be. It missed their covariances. Are you with me? Now, M+ doesn't do color coding like this. It would be nice if it did, but it does something sort of analogous. It prints for you something called normalized model residuals. So in the output, it is voluminous to get down to this point, and there are multiple kinds of model residuals. There's standardized and there's normalized. I'm going to point you towards the normalized. These give you the difference between the predicted covariance and the actual one divided by the standard error of the actual one. So these numbers are like z-scores. So any leftover covariance correlation that jumps out at you of more than like 2 to 3-ish is a problem. So let's find that output. It is on page 9 on the second part here. I'll get to the voodoo on the top in just a second. So this can get confusing in terms of terminology because the word residual is used in several different ways, even though it's the same word. So one of the estimated item parameters is item residual variance, right? That's not this. And then there's also residual variance versus regular variance. And then there's residual for the model, which means leftover or unmatched pattern residual. It's discrepancy. That would be a much better word than residual. But here's the correlation matrix that we just looked at. And here are the normalized residuals from M+ that take each of those correlations and essentially scale them as z-scores to indicate which of these missed correlations is relatively big. So the one that's off by 0.28 turned into a normalized residual of 6. The one that was off by 0.185 turned into a normalized residual of 4.7. So this is the analog to trying to figure out how to help your kid's report card. We have something that's more along the lines of report card 1, where there are particular holes that we need to address, particular sources of misfit, than report card 2, where it's just sort of generalized. And so what you would then do is going to be dictated by what that pattern is of misfit, of mismatch. Okay, with me? So what do you do? Well, M+ is going to help you and give you these very helpful suggestions. It can figure out, and it did, how much your chi-square would go down if you added each of these things to your model. So this set of results is what's known globally as a modification index. I refer to them as voodoo, in the sense that just because M+ suggested it doesn't mean it's a good idea. So what it is suggesting, for instance, sit 3 with sit 1 right here, and sit 2 with sit 4, with means a covariance. When it refers to the names of the original items, it's actually wanting you to covary their errors. So in this case, the highest modification index says that your chi-square of 309, or 307, excuse me, would go down by 161 if you just let these two items' errors covary. And the covariance between their errors would be this last number here, the standardized, this would be their correlation rather, 0.5, and their covariance would be 0.7. So it wants you to let 2 and 4 be related. It wants you to let 1 and 3 be related, even though 1 and 3 wasn't much of a problem. And some of the other relatively high numbers then correspond with the other holes here, 2 and 6, and 6 and 4. Yes?
So if you're defining the universe relationship based on the covariance, or with EPSY?
EFA would say that you need to have, so EFA doesn't allow error covariances of any kind. What EFA does is have multiple factors, and every item loads on every factor. So it's another way of addressing misfit, but in this model there is only one factor, so there is no opportunity to have other items loading on other factors because there are no other factors. So it's a different type of thing. So this modification indices get a bad rap because they are very sample specific. They're prone to type 1 error and all sorts of things that you would hear about in terms of adding stuff to your model that the data told you should be there that you didn't expect to be there theoretically. You want to tread carefully when you add these sorts of things. You have to be able to have anticipated it and defend it. It would be far better if you looked at the content of your items a priori, and if you saw something that was overly specific in 2 of them, then you can fit an error covariance that you anticipated as opposed to letting it tell you. There's a reason for it to be there. Likewise, if you have a test that has order effects, something to where a speeded test where you're asking people to compute measuring response time or something and they get better as they go along, you might include error covariances between adjacent items because there may be an additional pattern of relationship that has to do with the order of the item beyond just its content. So to the extent that you can hypothesize and anticipate extra relationships, it will give you a better shot at explaining them. In this case, though, it just wants me to stick in all kinds of error covariances, all kinds. Here are basically every possible one would give me a significant improvement in model fit. And every time you add 1, this list will change. So you can't just stick them all in at once and be done. So that's the next slide here. The higher the number, so the number in that first column is how much your chi-square value would go down. How much taller you can make HO.
So
the expected change in the chi-square. So in the M+ syntax, I asked for modification indices above 6.3 something. I have to remember exactly what it was. Let me look at that real quick. Hang on. I don't have my alpha of 0.01 chi-squares memorized like I do the other ones. Yeah, 6.635. So this command right here under output, that is asking for those suggestions to print any that have a chi-square difference, that first column, greater than 6.6, because each of these is 1 degree of freedom taken away by adding that new thing. And so that would make sure that it adds at least a significant difference in chi-square of p less than 0.01. That's where that number came from. The default is 10 if you don't list a number and you ask for this. This residual option right here, this is what gets you your normalized residuals so that you can figure out where the holes are in your predicted covariance matrix, where the discrepancies are. So only one person has children. Does anyone own a home? A couple people do. Okay. So when you buy a house, at least this was very common in other places I've lived, they want to sell you like a home warranty. Has anyone been approached with these? No? So when you list a house that's older, sometimes buyers will include a 1-year home warranty, where it's basically like if something breaks, you call somebody and they fix it for free. It sounds like a great deal. The problem is that they will always fix something. They will never ever pay for it to be replaced because they can always fix it. So you can have a furnace that stops working and you're freezing, and it will cost them, $3,000 to fix it, or you could have bought a new one for $4,000, and they will keep fixing it and fixing it and fixing it. That's the way this thing works. And so that's why some of these programs are not such a great deal. M+ is like this program. It will always suggest fixing your current model. It will never suggest that you just need a new model. So that's this list here. Because I only have one factor, the only thing it can suggest to repair my discrepant correlations is error correlations to fill in those holes. It can't tell me I need another factor, or that some of these items don't belong here. It will not ever suggest a new model. That's up to us. So what happens in terms of fixing misfit depends on these patterns. In this case, when you see the same items being implicated, that is a dead giveaway that you need a second factor. If those three have intercorrelations that are not predicted, and you can defend what that factor would be because they're worded differently in this case, it's actually forgiveness, I'm going to fit another factor and take out 2, 4, and 6 and put it on them. That's what I'm going to do. That is not always what you would want to do, though. We will talk later in the semester about bifactor models, which is another option, and what I actually ended up doing when I put together these 6 items with the other 12 that go on the rest of the scale. So, questions? So based on the pattern that I have more correlation in the data than is predicted amongst items 2, 4, and 6, and based on the fact that I can justify a second factor as being a separate concept, forgiveness as opposed to not unforgiveness, I'm making a 2-factor model. So I'm on page 10. So I now have, instead of just one sit, I have sit P and sit N for positive and negative. For convenience, for what's coming next, I have split out their intercepts onto 2 lines, their error variances onto 2 lines. Each factor now has a variance of 1 because I have to set a scale for each factor. Likewise, in the last line, each factor has a mean of 0 because it needs the other half of its scale through that. And then I have allowed a covariance between the 2 factors as this width. in the new model, I now have 19 parameters estimated. How many did I have before? Do you remember? 18. What's the extra one? The covariance between the factors, exactly. So another way of thinking about this two-factor model is that if I had said sit P with sit in at 1, given that these factors both have variances set to 1, that becomes a correlation. If I had said with at 1, I get back to my original one-factor model. So to the extent that the correlation between these two factors is less than 1, two-factor fits better than 1. So this is a nested model comparison. So now I need to augment my picture here. So I'm going to put a giant star up here above my old HO to say that this HO is significantly different than this H1. And now I'm going to put in a new one that is a little bit taller. Looks like a tooth, actually. HO. HO2. I'll make it water. Oh, wait. I know. Joke. So I'm trying to make it taller than my other one by adding one term to it. So what M plus is going to give me, though, is still, is my HO not worse than H1? Survey says 24. So I went from 307 down to 24. This 24 is still significant, though, although I'm starting to see some numbers inside my p-values. So my new and improved tooth model is still significantly worse than the best model, perfect model. But what I need to figure out is the difference between my old one and my new one. Did I make it better than what I had? Is the difference between 307 and 24 worth talking about? And to answer that, I have to do my own model comparison. So inside my spreadsheet here, M plus does not do this for you. You have to do it yourself. I'm looking at this set right here. So the first row is the one-factor model with 18 parameters. That's the HO log likelihood and scale factor from the output. Second row is my new two-factor tooth model, its new HO log likelihood and scaling factor, and then 19 parameters instead of 18. So the difference between these two, then, is a chi-square value of 341 from adding one thing, the factor covariance. And so this is a significantly better fitting model than what I had before. But it's still not perfect. So I'm heading in the right direction. That's what we know. But I'm not there yet, according to the overall chi-square of perfectness. So isn't perfectionism kind of bad? It's not a realistic goal to strive for, is it? Sometimes we just got to be good enough. So let's see if the rest of my output can make me feel better about not being perfect. Well, RMSEA. What do we want that to be? Small. How small? Less than 0.05 would be great. What do I have? Ta-da! 0.044. And I have a confidence interval around that of 0.025 up to 0.064. And I have a p-value that is non-significant, which means that my RMSEA is not different than 0.05. I win, at least according to that one. How about CFI? What do we want that to be? Big, yeah. We want it to be 1. What's a good CFI? 0.95-ish would be a really good one. That's a good one. How about TLI? Same metric, except it can go over 1. It also likes it. Next piece, chi-square test, significant. Do I care? Nope, I don't. This is the same number that was there before, because this is the difference between the worst and best models. It has nothing to do with mine. And last but not least, the root mean square residual. This is how far off, on average, your correlation is from between the model and the data. You want that to be little, 0.058, somewhere in there. This was definitely little. So by all of these additional pieces of information, this is a pretty good model. It's not perfect, but it is close fit. So I did the same thing then in terms of looking at the difference between data and prediction. So if we go to the correlation side, that's going to be easier to track. So here again, original correlation, same as before, that's H1. Here is my new predicted correlation matrix based on the idea that I have positive and negative factors coded in red and blue respectively here. And then here is the difference between what the model says and what the data say. These are all pretty small. The biggest difference is a correlation of just under 0.1. And in contrast to the previous pattern where there were these giant sources of discrepancy, these appear kind of like random, suggesting that there really are no big problems still lurking in terms of local fit. So here are my unstandardized results. Sit P by these items and sit N by those. These are my unstandardized factor loadings. Sit P with sit N. This is the covariance between the factors. And in this case, because the factor variances are 1, this is a correlation. So the correlation between my two factors is 0.56. I know that that is significantly less than 1 because my new two-factor model fit better than my previous one-factor model. So yes, forgiveness and not unforgiveness are not the same thing. Each item still gets 1 intercept. Each item still gets 1 residual variance. They should have gone down relative to the previous model. Because the model is fitting better, and the factor is responsible for relatively more of each item's variance than error. So here are my standardized loadings. These are all relatively healthy. The lowest one is about 0.6. I can live with that. Here are my R-squares. So those are the proportion of each item's variance that is attributable to the factor. Those are all nice and healthy. Lowest one is 0.35. So in thinking about effect size, you would report either the standardized loadings or the R-square. Loading squared is R-square. And there you have it. Let me fast forward a little bit. We'll go over omega in just probably next time. Here is my normalized residual matrix. So here's the original covariances. Here's the normalized residuals, z-scoring the discrepancies between the model predicted and the observed data covariances. And then here is my voodoo. So 4 things it is suggesting to me that would make my model fit better. The by statements on the top are cross-loadings. So it wants one of my positive items, number 2, to have an additional loading on the negative factor. So it would have 2 loadings instead of 1, and the additional loading would be negative. I have no idea what I would do with that. It wants 6 to go in the negative factor also, and it wants it to be a positive loading. Very small numbers, though. And it wants some more error covariances between 2 and 4 and 6 and 4. But note the size of these parameters. The changes in chi-square are much smaller than they were before. None of these things make any sense. None of these things I would have expected based on theory or logic or anything like that. So even though my model is not perfect, I am declaring it good enough. And most reasonable people, based on these numbers here, would agree with me. All right. So that's the world of local fit. Questions? Yes.
So, I think by reporting the result on two, I had to report the standardized result, or
Yes. Here's what you will report. Have you made it all the way to the back of the handout? Nope. So you're going to love this. Here, words. This is what you would report. So I wrote up the analysis. In reporting these models, the results sections are highly formulaic. There's usually an opening paragraph that describes the model you picked and how you identified the model, as well as the standards by which you are judging model fit. And then, what model did you fit first? What happened? And then what did you do next? So one-factor model was initially posited to account for the pattern of covariance across these 6 items, but it resulted in poor fit, as shown in Table 1. And so in your Excel sheet, I have labeled these. So here's model fit. If you have multiple models to report, it's nice to lay out their fit in a table so people can easily compare them. Although each item had a significant loading, the single factor did not fit. Sources of local misfit were identified looking at the normalized residuals, which were calculated as this. That way, if someone's not an M+ user, that you can still follow what you looked at. I'm identifying the fact that I found these extra patterns of correlation, that the model did not capture all of the correlation between 2, 4, and 6. And so I added to the model another factor that would do a better job. So then the necessity of separate latent factors for each type of item, positive and negative, was tested with a 2-factor model. And as I said, not unforgiveness, because that's what it means. And the 2 factors were allowed to correlate. The 2-factor model fit was acceptable by every criterion except for the significant chi-square, likely due to the large sample. I'm punting, because that's something that everyone will agree with, because it's a large sample. The correlation was 0.56, indicating that it was less than 1. Therefore, it looks like 2 factors to me. I looked at local fit, didn't see anything else that I could do anything with, and so I let it go. And so then I have table 3, which would look like this. So I have the loadings, the factor covariance, the intercepts, and the item residual variances. And I have the estimate and its standard error in the unstandardized solution, as well as the estimate and standard error in the standardized solution. So that's probably a bit more than you would typically see, but whenever you give a parameter, you need to give it standard error. P-values in this case are basically useless, so you can get rid of those columns. And then we talk about the stuff that we haven't gotten to yet. So note in the text, I've summarized the range of the standardized loadings. to give you a sense that if you don't want to look at the table, you can just look at the summary of the table here. And there you go. So then I have where these things would be, and you would always want to cite the software manual of the program that you are using. Does that help? Yeah, good. So yes, when it comes time for you guys to do homework 3, which is CFA on your own data, copy, paste, find and replace. If I see forgiveness in any of your write-ups, I will get very irritated. Unless you're actually looking at forgiveness. I know you've got some moral stuff in yours, right? But so this is a starting point, but you'll have to adapt it. In particular, the first paragraph is probably going to be pretty much the same except for the number of items that you have. The second paragraph, you'll report the fit of whatever factor structure you hypothesize. And then after that, it will become your own. So whatever you do to your model to change it, it doesn't necessarily have to become 2 factors. That was my solution because of the pattern I saw. I will mention, too, your job is not going to be to get good fit. Your job is going to be to go through the process and do what is reasonable. So if you change everything you possibly can that's reasonable and defendable, and it still doesn't fit, you will write it up and turn it in. Because I would much rather see that you understand that it doesn't fit and that you understand the numbers that tell you that than that you want to chase fit by estimating stupid models. That's not the objective. Okay? All right. Any last-minute questions here? Yes?
Do you have a model that's good general fit but bad local?
If it's big enough, yes. Because if it's a really big model, then the global fit is kind of like an average over the whole thing, and that average could conceal pockets of misfit. Other questions? All right, office hours start now. I will see you on Wednesday.